What we have here on these 5 screens is a physical representation of the network that Kieran has explained in the previous session. It's divided roughly into 2 halves. You can probably guess which the outside attacker half is. We have here a command and control center, which is out on the internet, and the server somewhere in the cloud that the attacker uses to host their malware. Behind the firewall, safe in the in the enterprise, we have an office PC, which could be used by administrators, DevOps, technicians. They get emails from the outside. They also need access to the OT side, the operational side, which this is a representation of the HMI, which controls which has access to the devices. Again, behind, it is partitioned off. So, the external attacker, they have no chance of accessing this kit here. The inverter, it is basically the proxy for the operational kit in the attack, which we'll show. And just to show how it works, we've got a basic HMI here with a very simple dial setting, where we can control the output of the inverter as it converts electricity from DC to AC. And the person who controls it, yeah, they think they have pretty good visibility of what's going on. However, the attacker has done their reconnaissance. They've identified in the email of someone who receives, perhaps they subscribe to a journal, their email appears on various wiki sites or support forums. So they know that this person is interested in this particular software, and they get an email one day which follows the usual format of the software they get from their vendor. And they take a look at it, and it says, update your software for this support package. Failure to do so may invalidate your support. So, okay, they do click on it, and they save the file. The file name follows the usual practice of their of the software from this vendor, and they install it, of course. Now, you might say, yeah, people don't do this, but they do. As we've seen from the many cases of ransomware in the real world, the Drydex phishing attacks on banks. And this follows the same sort of pattern that we saw, for example, in the Ukrainian attacks last year. So this is the command and control center. It has no victims registered with it at the moment, but that changes once we run the software that we've downloaded from this site here. So the patch, once it's applied successfully, we click on that, a new entry appears here on the command and control. This person out on the internet now has visibility of what is happening inside the enterprise. We right click on that, and it has a very full set of functionality to access. For example, if we look here, we can access the remote desktop, remote webcam, the file manager of the system, start up a remote shell, capture sound, if you just want to listen to what's going on at the board meeting or what they're chatting about, a keylogger, stored passwords. But in this case, we'll start up a remote password or a remote desktop. So the person on the outside, the attacker on the outside, now has not just read access, but the ability to modify this this screen. And I think one of the precursors for the Ukrainian attack was operators noticing that the cursor was moving, but they weren't moving the mouse. So that's obviously an obvious indicator of some sort of attack. Now, we've moved inside, so this is a bigger screen, so I'll use it. But the attacker, imagine this is the attacker, who now he's learned a bit about the organisation and what their work practices are, and he realises that this is an internal internet website, and it monitors the equipment on the operational side. And there's the opportunity to put in an IP address in this field and enter some input. And yeah, okay, that's very useful. It works. They can submit a query. It's processed by the internal website, and it goes to the operational side, gets back the information that's needed, and everything is fine and dandy. However, the web application written in probably PHP, it has a few weaknesses on validating that input. And there's a host of opportunities at this stage for attacking internet websites, SQL injection, cross-site scripting, and so on. This particular attack is based on a feature of Linux, where what we want to do is append some Linux commands. We know the enterprise server is Linux-based, so we append some commands that are going to start up a shell on the enterprise and basically pipe the output to an external attacker's machine in the cloud. So this is this screen here where the attacker is listening on a particular port. They can't get in through the firewall, but rather lax operational procedures here allow us to put in this command and allow the attacker to establish a shell on an internal machine that has access to the operational network. So what they will be able to do is perhaps escalate the privilege, look at the file system, look at the network traffic, and in this case, what we've done is we've added a GUI to make it a little bit easier to see. But the attacker at this point would probably just stay on the command line interface and start reconnaissance on the network and attacking it. So I'm going to move from the Office network to the actual enterprise machine that straddles the Office network and the operational network, because that's where the man in the middle is going to sit. He's going to have visibility of the traffic from the HMI and the traffic to the PV inverter and manipulate that traffic. So at this stage, everything's still fine. The chap here, he still has control, so when he sets the value here, yeah, the bar goes up, fine. So let's start the attack. We use some magic here, start up our man-in-the-middle agent, and they've now established connections outbound with the man-in-the-middle application here. So let's just check that we've still got traffic. Yeah, we're still in control. The command bar goes down. But we've seen that traffic now. We select those devices and we say, no, let's do something different. We want to, say, turn this device off. So if we set its output to less than 10%, the device will go off. So let's put 5 in there and do a set command. Now, the agent inside the network has that value. It hasn't yet acted on it. What we need to do is the operator on the HMI to change a command and say it's a nice sunny day, demand is high, it's coming up to lunchtime, lots of electricity is required. So we put the output up to 96%. So we're expecting the yellow bar to go up, or the orange bar to go up to there. So we do set value. It's not going to happen. It's gone to 5%. The HMI, yeah, they think everything's fine, but as the phrase we heard in the previous 2 days was, the buildings are burning in the background. The system is not under the control of the operator. So, what can we do about it? Well, one of the unobserved by yourselves, we've been capturing this traffic and monitoring it on a monitoring system on the IDS, which Bujun has
So yeah, we were watching on what Ivor was doing all the time. So IDS is located in the same network and monitoring all the traffic and displaying the information in the web interface. So on the top, you can see the volume of the traffic, right? So when you submit any request, they will count the number of traffic and show it. So as you remember, on the rightmost 3 bar graph showing number of traffic, which is before the millimeter attack, we changed to wise the value for the power limitation. You can see number 2 and number 2. And the last one is the change the power limitation to 80 something after MITM attack. You can see the number of traffic has been doubled because man in the middle, that guys receiving the packet and deliver to the device as well, then it will be duplicating the traffic for make them believe they are talking to each other. If I don't send it, if I don't deliver it, they will find out I don't get I don't get any traffic from the HMI device. They will find out something is going wrong in the network side. So we can see the duplication in there. And also the other information can be displayed. So in that case, we are displaying what kind of MMS packet has been delivered. In this case, wide request and wide response. And also, we set to, attacker tried to set the power limitation below to 10, which is, we are assuming that is critical status for the PV inverter. So we define the rule to detect those activities. And the alert side, they show the lower active power limitation has been transmitted to the device. We are giving them. So that alert can go to the resilient control to have some other process, or we can deliver it to the firewall to block the traffic. So anything can be whatever you want. And at the bottom, they show the IP address, and it can be used for whitelisting or whatever. So that was the IDS was doing for all times.
Yeah, this is, if I may, this is when you have the, what I'll say, the relation between the control system and the controller, set of controller in the field. What happens if someone attacks the bottom part? So you don't have any control because this is a closed loop control. So someone attacks on that level. So the system will not react properly. I mean, that's why I should from that.
It's a good point. So because this is NIDS, Network Intelligence System. We are looking at the network side. If the device doesn't have any interface or remote connection and connected to the network, so we will not see that. Then in that case, we should have some local control in their own. So that's another perspective of security. That's important.
Okay. Just want to show.
And we will show another attacker. We show the MITM, but we also have the MMS scanner I mentioned at the last slide of the presentation downstairs. So if we start scanners, please.
Okay, it's interesting just to note before the attack, on the left-hand side, the x-axis is a maximum of 4. So once you start scanning and exercising, doing a low-level attack, it goes up by 2 orders of magnitude. So you can see some of the traffic here. It's exercising the 61850 model, the tree of functional level, much more deeply, and basically just doing a tree search and values.
Yeah, you can see the surge at the volume of the traffic. That could be the evidence of someone is scanning the networks and doing. And also you can see different types of MMS requests as well, not only the write or route request on response. You can see many different requests from the scanner. So, and the different IP addresses are there in the bottoms. So the IDS can find out those scanners as well to indicate someone is sitting down there and doing something bad.
Or firmware updates. That will be another significant event that should be detected.
Okay, so the first thing we showed you was the man-in-the-middle attack, because that's, I guess, the most interesting. It's got a physical effect. But probably if there was an attacker in the network, they would do some scanning first. So the scanning that you saw there was a large burst of traffic, but they would probably send it out a bit more slowly. Maybe they'd be looking for some specific fields that they knew were being used from other reconnaissance. So it might not be as intense as that. But the important thing for that is that you can see what the normal traffic looks like. You can build up a normal profile. And then in the future, try to detect is something abnormal here. So the next thing I want to show you is, got one more slide. So,
Or last slide.
last slide, one last slide. So the question is, so what? So what we want to do is move beyond just generating intrusion detection alerts that appear at an operator just goes, well, that went wrong. We want to move to a system that can be more resilient and take action whenever these alerts are generated. So in another part of the project, KDH, the university, are developing resilient control. So this means that if it gets some information that the underlying system may be under attack, it takes some action in the control of itself to try and mitigate that, possibly ignore the information it's getting from the network, and put the system back into a default state, which you know is safe. So in this example on the screen, you can see a project that's being undertaken in parallel with Sparks by AIT. So just to explain a little bit, AIT has two departments we're working with. So Paul is working at the security department. There's also the energy department. So separately they're working on this test bed. So this time in the train, we're looking at these yellow dots are PV installations. So for each of those, you can imagine we're monitoring them. And the setup there is thinking about the future smart grid. So not just the grid today, the grid tomorrow, imagining it's maybe more federated, so the grid can be composed of different microgrids. It could potentially also have a lot more embedded generation. So here we're thinking about a lot of solar generation, it could be wind. So going from a big monolithic system to something that's got more distributed generation. So the use case here is that the PV arrays are being used for voltage management. So changing the reactive power from the PV to adjust the voltage depending on the current state of the system. So you can imagine there in the bottom left there's a long red line down to a set of 6 PVs there. So you could set the reactive power there different than at another point on the network. So the research there is really to look at that from a power systems perspective. So what we're doing is trying to come along and say, okay, before you would roll out that system, what would an attacker do to it? What can we do now when the system is being built to try and make it secure? So a traditional kind of poor approach might be that you have a flat IP network. So all of those solar panels are connected to, say, a 192, 168 kind of local area network, all hanging off one switch. So you should be really segregating that, and then the segregated zones should be monitoring. So if we would have an IDS, say, in that bottom corner, the top left-hand corner, top right, each of those would be treated as separate areas of the grid. If our IDS detected unusual scanning in the, say, bottom left section, we alert the resilient control, and it tells those local systems, okay, I'm getting information that the IT system may be under attack, or an attack could be about to happen. I'm going to set those devices into a known safe state, so the control acts locally rather than centrally. So we take the control away from the central IT network system. So the objective here is to not just have the IDS generating alerts, but implement in a system where the system itself takes action based on the IDS. The traditional question is, well, if you've got an IDS, can you block packets? Is that not dangerous? So in this approach, you get around that. So you're not blocking packets, you're just setting that part of the grid into a known safe state. It might not be optimized, it might not be the best in terms of generation, in terms of making money for the grid, but it's safe, and you can then investigate what's going on until you figure it out and reconnect and control the centralized manner. Okay, so hopefully that gives you an idea of where we're trying to go and what the whole system together does.
Question: red string doesn't exist.
Okay.
That's invented. Or does it exist?
It exists, yes.
Where it is? In
It's in Austria, yeah. So it's just a use case that they're using. So I think the project is to look at how they would implement this for real in the town. But so the test environment itself is based on taking that and mapping it to some simulation labeling and some real in the loop. So the PV array, there's the inverter part of this bit as well.
Some PVs exist already. So you really will take over. You're taking the real data in your simulation.
Yeah, so it's based on the real system, the real technology, and the real network.
But you will not interfere.
No, not the,
This is TRL 4, maybe.
we won't
While
exactly
it's TRL 9 or something will be mature enough for
Exactly.
maybe do a pilot testing.
So this is one of those things which were in the last 7 months of the project. So this is that exciting phase where 6 months ago somebody goes, yeah, we could combine these. And I go, yeah, let's see how that goes. So we're now in that stage of, okay, let's take our different parts and combine them together and see if we can do something actually really novel and bring it.
How many false positives?
We don't know yet. So we're still in the stage of trying to bring it together and integrate it into the lab setup. So once we have that running, we can tell you about false positives.
The false positive for the IDS depends on what detection mechanism you are using. If it is a normal detection, it's not sure this is attack or not, just this is suspicious, right? But in terms of the whitelisting and signature or state analysis, we need expert knowledge to develop those rules. So it will reduce the false positive or false negative. So it should be highly skillful person has to derive the rules, then it will reduce the false positive.
So the problem will be that
Yeah.
while you're deriving the rules,
Yeah, so I believe we try to reduce the gap between those security experts for the IDS and the system designers. Then that is why we focus on I6150. So I6150 has the capability of providing some description for the system to implement their own system. So from that system description, we can derive those rules and we can run it on the IDS and give some order to the region control and whatever other control loops. So that's another our focus on this project.
yes, one of the problems will be that as you're developing the rules, people are developing new software, so traffic, the signature of the traffic will keep changing.
Yeah.
So how fast can you develop? How fast can you learn and say, yes, this is normal, by the time they're already rolling out the new software?
Yeah, that's right.
Now it's different.
So we are developing multi-attribute SCADA IDS. So for the non-attack, we have to keep updating our rules, signature, whitelist. And we also try to have the automatics as well. That it will cause some false positive, but it is try to find out the unknown attack, unknown vulnerability in a short time. Not just sit down and waiting. Someone is giving us this is new signature. Use it, please.
Yeah, indeed, there is a structural problem. The attackers are always one step in advance before the defenders. That's it.
But there are also signatures that not necessarily can be changed. When we talk about signatures, we don't talk about the pattern of events. It's also related to the protocol itself.
Yeah.
Signatures and headers of the protocols, it can't be changed.
That's another problem is you have a protocol in order to understand yourself, but bad guys can use it at the same time, so it's transferred. We had in another case, in another project, 50% project as well, the considerations how to come around that and try to do it. And as far as I remember, it wasn't a very wise solution found yet. So if you find something like that, excellent.